Hello students, in this video I am going to discuss how to calculate distance of closest approach, and we will learn how to calculate the radius with the help of mirror nuclei method. So basically we are going to find out how to calculate distance of closest approach as well as nuclear radius with the help of mirror nuclei method. So first I am going to discuss distance of closest approach. So first topic today we are going to discuss is distance of closest approach. Closest approach. So first we have to learn what is the meaning of distance of closest approach. Distance of closest approach was first time calculated by Rutherford with the help of his famous alpha scattering experiment by a nuclei. So when he was studying this alpha scattering experiment, he was the first person who have calculated the distance of closest approach. Now question arises, what is the meaning of distance of closest approach? Suppose we have a nuclei here. Suppose this is the nuclei here. This is positively charged nuclei. And suppose an alpha particle. Here we have an alpha particle which is moving in the line of this nuclei. So basically an alpha particle is moving towards the nuclei, and we assume that the kinetic energy of this alpha particle is suppose K alpha. So what we have an alpha particle which is moving towards the nuclei. And suppose charge on this nuclei is plus Z. Z number is the atomic number of the nuclei or charge number of the nuclei, and this alpha particle with kinetic energy K alpha is approaching towards this nuclei. Then what will happen? This alpha particle is positively charged particle. This alpha particle is also positively charged particle. Positively charged particle. Initially, the kinetic energy of this alpha particle is K alpha. This is the kinetic energy. This is the kinetic energy of the alpha particle. Now, when this alpha particle will move, towards the positively charged nuclei, then what will happen? This is positively charged particle, this is positive nuclei. So basically a repulsive Coulombian force will act between them. So when this positively charged alpha particle moves towards the positively charged nuclei, then Coulombian force, repulsive Coulombian force will go on increasing. So when this particle is moving towards the nuclei, then Coulombian repulsive force increases. And when this is moving towards the nuclei, because Coulombian force is acting between them, as a result of this Coulombian repulsive force, kinetic energy of alpha particle decreases. Kinetic energy of alpha particle decreases, while the Coulombian repulsive potential energy increases, while repulsive Coulombian potential energy, repulsive potential energy increases. So what is happening? What is happening here? When alpha particle is moving towards the positively charged nuclei, then a Coulombian force is acting between them. They are repelling each other. When they are repelling each other and this alpha particle have to move towards the nuclei, so this alpha particle is acting against, it is moving against this repulsive force, as a result of which its kinetic energy will decrease. But as this particle is moving forward, the distance or the separation between these two particles, alpha particle and this nuclei, it is decreasing, as a result of which repulsive potential energy is increases. And at a time and after this movement, after this journey, a time will come when kinetic energy will become zero. So a point will, this alpha particle will achieve a point where its kinetic energy will become zero. Kinetic energy will become zero. But it will have maximum, here kinetic energy is zero, but here at this point maximum repulsive potential energy will be there. So here at this point, when this kinetic energy becomes zero, potential energy maximizes, or potential energy achieves the maximum value. So here at this point, for a moment, this alpha particle will be at rest, but still it is observing a repulsive force. So as a result of which, after that moment, it will retrace its trajectory. It will be repulsive. It will start moving in the backward direction. So this alpha particle will move in the backward direction after this point where kinetic energy becomes zero, but potential energy becomes maximum. Because here kinetic energy is zero, this alpha particle for a moment, it will be at rest. When it will be at rest, but still it is experiencing a repulsive force, so automatically it will start moving in the backward direction. Now it will start moving in the backward direction. So this is the distance. This distance, separation between this nuclei and the point where the kinetic energy is zero, separation between these 2 points. This is known as the distance of closest approach. Suppose this distance is, suppose R0. Yeah, I can assume this as X0. Suppose X0 is the distance of closest approach. So what is happening here? We have launched a alpha particle with kinetic energy K alpha towards a nuclei. But as it is moving in the forward direction, it is experiencing repulsive force. As a result of which, this K alpha will go on decreasing. It will decrease, and it will reach at a point where its kinetic energy will become zero. But when kinetic energy will be zero, at this point potential energy will become maximum. Potential energy will become maximum, or you can say this kinetic energy of the alpha particle, it will convert into the total kinetic energy, will convert into the potential energy, repulsive potential energy. So at this point, this potential energy will be equal to the kinetic energy, initial kinetic energy of the alpha particle. At this point, this alpha particle for a moment, it will be at rest, but it is at rest, but still it is experiencing a repulsive force. Repulsive force between positively charged alpha particle and positively charged nuclei. So due to this repulsion, it will start moving in the backward direction. So the separation between this point and the center of nuclei is the distance, is the minimum distance which this alpha particle can move towards, or it can achieve towards the nuclei. This alpha particle cannot move ahead of this point because its kinetic energy becomes zero. Only if you are increasing initial kinetic energy, if you will start increasing this initial kinetic energy, it will further move in the forward direction. So this value x0, this depends upon the initial kinetic energy of the alpha particle. So we can calculate this distance x0, which is known as distance of closest approach, by the condition that at this point initial kinetic energy of alpha particle will be equal to the potential energy at this point x naught with respect to the center of this nuclei. Suppose Ke, kinetic energy of the alpha particle is K alpha, and the potential energy at this point will be equal to 1 upon 4 pi epsilon naught. Charge on this alpha particle will be plus 2e, while charge on the nuclei will be equal to plus Ze. So this will be 2e into plus Ze divided by the separation between these two particles, this pi alpha particle and this nuclei. This is x naught. So by using this equation or equating the initial kinetic energy of the alpha particle with the potential energy of the system of the alpha particle and nuclei at this distance of the closest approach x naught, we can find out the value of x naught. So there can be a numerical in the exam on the basis of this formula. This formula is very important to calculate the distance of closest approach. So Rutherford was the scientist. Rutherford was the first person who was able to calculate this x naught, distance of the closest approach, with the help of this formula. He has devised this formula to calculate the distance of closest approach. For example, suppose we are considering an alpha particle. Suppose take an example here. Take an example, numerical example here. Suppose we have an alpha particle. We have an alpha particle which is moving towards the nuclei. Whose Z number is 20. Suppose whose Z number is 20. So alpha particle is moving towards a nuclei whose Z number is 20. Now we have to calculate this distance of closest approach for this case. So here this will be K alpha. We will use this formula, K alpha equal to 1 upon 4 pi epsilon naught. This will be 2Z E square upon x naught. This will be 2Z E square upon x naught. Now what will be the value of K alpha? K alpha, if this is a non-relativistic case, then this will be half of m alpha V alpha square equal to 2 times Z E square upon 4 pi epsilon naught x naught. Now suppose what will be the value of this alpha, mass of the alpha particle? Mass of the alpha particle will be equal to 4 times of the mass of the proton, 1.66 into 10 power minus 27 kg. Why this is? Because alpha particle is 2He4, A number is 4. So basically its mass will be nearly 4 times the mass of 1 AMU. So this will be 4 into 1.66 into 10 power minus 27 kg. Suppose V alpha here is 10 to the power 7 meter per second. This is 10 to the power 7 meter per second. This is the value of V alpha. You are well aware this Z is equal to 20 here. What is the value of E? E will be equal to 1.6 into 10 power minus 19 coulomb. This is the value of E. And 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught. What is the value of 1 upon 4 pi epsilon naught? This value is equal to 9 into 10 to the power 9. This value is equal to 9 into 10 to the power 9. So this value is 9 into 10 to the power 9. Now substitute all these values here. If you substitute all these values here, then you will find out that this x naught for this problem comes out to be 1.5 into 10 to the power minus 14 meter. This will be 1.5 into 10 to the power 14 meter. So this is the value. This is the value. of this problem. Similarly, you can consider another case. If you consider that Z equal to 79, if I consider Z equal to 79 and all other parameters remain same, then this x naught comes out to be 5.9 into 10 to the power minus 14 meter. So from here, with the help of this formula, one can find out the value of x naught, where x naught is the distance of the closest approach. Distance of the closest approach means if we have an alpha particle of a particular kinetic energy, then it will move toward, if this is moving towards the nuclei, then the minimum distance, minimum separation possible between the alpha particle and nuclei, that is known as distance of closest approach. So we can calculate this distance of closest approach in this form. So what is the importance of distance of closest approach? What is the importance of this distance of closest approach? Distance of closest approach tells us that radius of the nuclei will be less than x naught. Radius of the nuclei will be less than x naught. So here this is 5.9 into 10 power minus 14. It means this radius of the nuclei will be less than this. So by doing this experiment many times, basically Rutherford was reached to the conclusion that radius of a nuclei is of the order of 10 to the power minus 15 meter. So basically Rutherford was the first time who first time estimated that or predicted that the radius of the nuclei is of the order of 10 to the power minus 15. He has used this method of calculating distance of closest approach. With the help of this method, he was not able to calculate the exact radius, but basically he was providing us the information that the radius of this nuclei will be less than distance of the closest approach. Radius will be less than the distance of closest approach. If you will start increasing the kinetic energy, then what will happen? If you will increase the kinetic energy of this alpha particle will reach more and more closer to the alpha particle, or to this nuclei, this alpha particle will reach more and more closer to the nuclei. So on the basis of this, we can find out the distance of closest approach for different nuclei, as well as for different values of kinetic energy. And by using this relation that radius of the nuclei will be less than the distance of closest approach, Rutherford concluded that the radius of the nuclei is of the order of 10 to the power minus 15. This was the first time someone has predicted the size of the radius, so size of the nuclei. You can solve a numerical here. I am giving you a numerical. We will use this formula to calculate the distance of closest approach. So I am giving you a numerical here. Question is, this is example number 2. This is example 2. Here, calculate the distance of closest approach. Calculate the distance of closest approach. Closest approach for protons of 1 MeV energy, when meeting Rutherford scattering when meeting Rutherford scattering by nuclei of gold, nuclei of gold, Z equal to 79. So you have to calculate the distance of closest approach for this case. So again we will use this formula K alpha equal to 1 upon 4 pi epsilon naught. But here what is the particle? These are protons. In the earlier case, this formula was for alpha particle. Alpha particle was approaching towards nuclei. Charge on the alpha particle is plus 2e. But here they are using protons, and charge on the proton is plus e. So this will be the modified formula. Here this will be the kinetic energy of proton. So kinetic energy of proton will be equal to 1 upon 4 pi epsilon naught. This will be plus e into plus Ze upon x naught. So this Kp, how much is the value of, or how much is the value of this Kp? This is 1 MeV. This is 1 MeV. And before substituting these value, I will like to replace this, or I want to rewrite this formula as this will be E square upon 4 pi epsilon naught Z upon x naught. I am rewriting this formula in this form. Why I am rewriting this formula in this form? Because the value of this constant E square upon 4 pi epsilon naught, this is equal to 1.44 MeV Fermi. This is the standard value you can remember. That value of this constant term E square upon 4 pi epsilon naught is equal to 1.44 MeV Fermi. So what is the advantage here? This kinetic energy is given as 1 MeV. So left hand side is in MeV. Here I can write this 1.44 MeV Fermi. MeV Fermi. And here this will be Z. Z will be equal to 79 upon x naught. This will be 79 upon x naught. So here this MeV will be cancelled out. This MeV will be cancelled out. And what will be the value of this x naught? This will be 79 into 1.44. Now this will be in Fermi. This will be in Fermi. So here this is in Fermi, so automatically this x naught, whatever value will come out for this distance of closest approach x naught, this will itself be in Fermi. So this is a method in which you can directly substitute the value of, E square upon 4 pi epsilon naught, whose value is 1.44 MeV Fermi. So this will be a great help for you people. If you calculate this value, this value will come out to be, this will be equal to, I think, this will be roughly 80. So this will be nearly 120 Fermi. This will be nearly 120 Fermi. So this will be the distance of closest approach. This will be the distance of closest approach. If you calculate this, this will be 114, nearly 114 Fermi. This will be the answer of this question. So this type of question can be asked in the exam. This is an important question. Now come to the another topic. That is very important from exam point of view. So this is mirror nuclei method. This method is, another topic is mirror nuclei method to find out the radius of the nuclei. Mirror nuclei method to find out the radius of the nuclei. Next method is mirror nuclei method. Mirror nuclei method. This mirror nuclei method is used to find out the nuclear radius. This is used to find out nuclear radius. So First question arises, what is the meaning of mirror nuclei? What is the meaning of mirror nuclei? First we have to understand the meaning of mirror nuclei. For this, I am writing few examples of mirror nuclei like 1H3 and 2He3. 1H3 and 2He3. These are the examples of mirror nuclei. 1H3 and 2H3 is an example of mirror nuclei. Another is 3Li7 and 4Be7 This is another example of mirror nuclei like 6C13 and 7N13. This is another example of the mirror nuclei. And another example is 19K39 and 20Ca39. These are the four examples of the set of mirror nuclei. These are the examples of four set of nuclei. So can you observe few things about mirror nuclei? Can you observe anything? This is a set like 1H3 and 2He3. This is a set of mirror nuclei. So here, why they are known as mirror nuclei? Because if you write down the number of protons here, number of proton is 1 here, and number of neutron is 2. While in case of helium, you will find out number of proton is 2, while number of neutron is equal to 1. So in this type of nuclei, number of protons and number of neutrons, they are exchanged. So here this was 1, 2, and here this is 2, 1. Number of proton becomes number of neutrons here, and number of neutron becomes number of protons here. And another important thing is that NP minus Nn, number of protons minus number of neutrons, will be equal to plus minus 1 only. So difference between number of protons and number of neutrons is equal to 1 for mirror nuclei. So this is a set of mirror nuclei. So in case of mirror nuclei are those nuclei in which the difference between number of proton and number of neutron is 1, as well as number of protons will become number of neutrons and number of neutrons will become number of protons. In case of mirror nuclei, their number of proton and neutrons are exchanged. In case of mirror nuclei, you can consider this case like number of proton is here 19, number of neutrons is 20. This is 39 minus 19, so this will be 20. While here number of protons is 20, while number of neutrons is 19. So number of proton and number of neutron are exchanged, as well as difference between number of proton and number of neutron is only 1. So NP minus Nn is either plus 1 or minus 1. So their difference is equal. So this type of nuclei where number of protons and number of neutrons they are exchanged, as well as difference between number of proton and number of neutron is only plus minus 1. These type of nuclei are known as mirror nuclei. And these sets of the mirror nuclei can be used to find out the nuclear radius. So these type of set of mirror nuclei can be used to find out the nuclear radius. How can we use these mirror nuclei? How can we use these mirror nuclei to calculate the nuclear radius? Consider an example of 7 and 13. This 7 and 13 is an unstable nuclei. It decays via beta decay. It decays via positive beta decay, and it will convert into 6C13. It will convert into 6C13 plus E plus positron plus neutrino. Whenever in a beta decay, if positron is emitted, then this positron is always An associated particle that is emitted, that is known as neutrino. This is neutrino. So with positron, another particle that is emitted by the nuclei, that is known as neutrino. So this is a beta plus decay process for this 7 and 13, which is a unstable nuclei, and this will convert into 6C13. Now this 7 and 13 and this 6C13, they are mirror nuclei. They are mirror nuclei. They are a set of mirror nuclei. Now these two nuclei, now this reaction and this set of mirror nuclei can be used to find out the nuclear radius. How can we use this reaction? How can we use this beta decay reaction to find out the radius? So first consider this. First consider this 7 and 13. First consider this 7 and 13. So 7 and 13 has number of proton will be equal to 7. While number of neutron is 6. I can write this 7 as 6 plus 1. I am writing this 7 as 6 plus 1. And here in this case of 6C13, number of proton is 6, while number of neutron is 7 here. And again I am writing this 7 as 6 plus 1. 6 plus 1. So you can find out, you can observe one thing, that this 6 proton and 6 neutrons are common on both sides. Only here we have one extra proton and here we have one extra neutron. Here on the left hand side we have one extra proton, on the right hand side we have one extra neutron. So we can also write this equation in this form, that proton is converting into a neutron plus this positron plus this neutrino. This is known as positron. This E plus, this is known as positron, and this is known as neutrino. This is known as neutrino. This is known as neutrino. So we can also write this equation in this form, that proton is converting into neutron, but this process is taking place inside the nuclei. I'm not saying that this P is free proton. This is not a free proton. Rather, inside the nuclei, proton is converting into neutron, and at the same time a positron and this neutrino particle is emitted. So now come back to this reaction. Come back to this reaction. In this reaction, how much energy will be released? In this reaction, how much energy will be released? How much energy will be released? Energy released here, total released energy released, delta E, will be equal to the change in binding energy. This will be change in binding energy. So how much energy will be released? This will be the binding energy. This will be equal to the binding energy of this C13 minus binding energy of this N13. Binding energy of C13 nuclei minus binding energy of N13 nuclei. Now what is the formula for binding energy of this C13? What is the expression for the binding energy of C13? What is the formula? What is the formula? Basically, binding energy of any nuclei is made up of 5 components. First is known as volume energy. This is EV. This is EV, binding energy, volume binding, basically volume energy, minus, next term is surface energy. This is for C type of nuclei, C13, minus this Coulomb energy. Third is Coulomb energy, minus asymmetric energy. Asymmetric energy, and this will be here this will be plus minus, this will be pairing energy, this will be pairing energy, this will be pairing energy. And because this is odd even nuclei, for a odd even nuclei, for odd even nuclei, for odd even nuclei, this pairing energy E delta, this will be 0. What is the meaning of odd even nuclei? Odd even nuclei or even odd nuclei means out of this number of proton and neutron, one is odd number, another is even number. Here this is even, this is odd. So this is even odd nuclei, and here this is odd, this is even. So they are even odd nuclei or odd even nuclei. For even odd or odd even nuclei, this E delta or pairing energy term, this is 0. This is 0. So I am removing this term. So basically here there will be 4 terms here. This is known as volume energy. This is known as volume energy. This is known as surface energy. This is known as surface energy. This is known as Coulomb energy. Coulomb energy. And this is known as asymmetry energy. Asymmetry energy. This is the binding energy for this C13, this C13 nuclei. This is the binding energy for C13 nuclei minus binding energy of N13 nuclei. This will be volume energy EV for N minus surface energy for N minus Coulomb energy for N13 and minus asymmetric energy for N13 nuclei. Out of these nuclei, out of these 4 terms, this volume energy term, this surface energy term, and this asymmetric energy term, these 3 terms, out of these 4 terms, these 3 terms, EV, ES, or this asymmetry energy term, they are only depending upon A value. They are depending upon A value. What is the value of EV? EV value is equal to AV into A. This is not depending upon Z. This is not depending. EV is depending upon only A, and A number is same. Here A number is 13. This A number is same. So automatically these 2 terms will cancel out. These 2 terms will cancel out. Similarly, this ES, surface energy term, ES, this is written as minus, this is written as AS, A to the power 2 by 3. It is also depending. It is also depending upon the A number, mass number only. It is not depending upon Z number. This is not depending upon Z number. So, because A number is same for both the nuclei, so this will also be cancelled out. So, volume energy term and surface energy term will be cancelled out. Now, come to this EA, asymmetric energy term. This EA, this is equal to A minus 2. This is equal to number of proton minus number of, or you can say number of neutrons minus number of proton square upon A into some constant A into A. So this is a constant here into Nn minus Np square upon A. So here, in case of mirror nuclei, in case of these 2 nuclei, you will find out that here Nn minus Np is minus 1 and here Nn minus Np is plus 1. So here we will substitute either plus 1 or minus 1. So if you substitute either plus 1 or minus 1, you will find out the same value of EA. So this EA will also be cancelled out. So I am cancelling these 2 terms because AA, either you write +1 or -1, value will be same. Value will be just AA upon A. So this will be same for both the nuclei. So these three terms will be cancelled out. So these terms will be cancelled out. And what will be left here? What will be left here? It will be Coulomb energy term for N13 minus Coulomb energy term for C13. So volume energy term, surface energy term, asymmetry energy term, they will be cancelled out for both the nuclei. Only these Coulomb energy term will survive. So here this will be EC for N13 minus EC for the Coulomb. So here I can rewrite this equation. You can note down this, and I can again rewrite this equation that delta E is equal to delta BE, change in binding energy. So whatever is the energy released in this beta decay reaction, this will be equal to change in binding energy, and this will be equal to change in Coulombian energy term. Change in the Coulomb energy of both these nuclei. So this much amount of energy will be released. So this much amount of energy will be released in this beta decay process. So energy released in the process, delta E, will be equal to change in binding energy, and this will be equal to change in Coulomb energy term. Change in Coulomb energy term. So what is the expression of Coulomb energy term? What is the expression of Coulomb energy term? You can remember this. You can remember this, the expression of Coulomb energy term. This is equal to 1 upon 4 pi epsilon naught 3 times Z square E square upon 5R. This is the expression of Coulomb energy for any nuclei. For any nuclei, this is the expression of Coulomb energy. This is the expression of Coulomb energy for any nuclei. So if I substitute this expression here, then energy released in this beta decay process, which is equal to change in binding energy, and this will be equal to delta EC. This will be equal to, so this E square, I can write this E square here. So this will become E square upon 4 pi epsilon naught here. And this will be 3 times Z1 square minus Z2 square upon 5R. Where Z1 is this one. Z1 is the atomic number of this nuclei. In this case, this is N13, so Z1 is 7, and this Z2 is the atomic number of this second nuclei, which is 6 here. So this will become 7 square minus 6 square divided by 5R. Here R is same for both these nuclei. Can you tell me why this R is same for both these nuclei? Can you tell me why this radius will be same for both these nuclei? Because radius is given by R equal to R naught a to the power 1 by 3. 1 by 3. Because A number is same for both these nuclei, so this R will be same. So radius of the nuclei will be same for this N13 and this C13 nuclei. So this is the radius of both these mirror nuclei. So this is one part. If they are giving you a numerical in which they are saying that okay, this is the beta decay process, and in this beta decay process change in Coulomb energy is suppose 4 MeV. Suppose they are providing you the change in the Coulomb energy is 4 MeV, and then you have to calculate radius. Then this is very simple. What you will write here? You will write 4 MeV here. What is the value of this E square upon 4 pi epsilon naught? This is 1.44 MeV Fermi. This is 1.44 MeV Fermi. And here this will be 3 times And Z1 square is how much? This is 7 square. 7 square minus 6 square upon 5r. Upon 5r. So by solving this equation, by just solving this equation, you can find out the value of r, and this r, the unit of this r will be equal to Fermi, because this MeV will be cancelled out here, and to satisfy the dimensions, this r should be in Fermi only. So when you will solve and you will find out the value of r here, so whatever value you will get, that will be in Fermi itself. So by using this expression, you can solve this type of numerical. So if they are providing you the change in Coulomb energy, what is this? This is change in Coulomb energy. This is change in Coulomb energy. Coulomb energy. Then you will use this formula. To calculate the radius of the nuclei. The radius of the nuclei, basically nuclear radius of the nuclei. So this type of numerical can be in the exam. Now come to the next part of this mirror nuclei method. There can be some another type of numerical in which they will provide you. There can be another type of numerical in which they will provide you the maximum kinetic energy. Maximum kinetic energy of this positron, E positive particle. There can be a numerical in the exam where they will provide you the maximum value of the kinetic energy of this positron, and they will ask you to calculate the nuclear radius. How will you do this? How will you do this? So basically we have to consider another aspect of this process. We have to consider another aspect of this process. So this is a beta decay process. This is a beta decay process. In this process, energy is released. How much energy is released? That is delta E equal to delta BE, change in binding energy. Whatever is the change in binding energy of these two nuclei, that will be this released energy will be equal to this. This will be equal to, we have calculated that this will be equal to delta EC. Delta EC. Now this energy is released. Now this much amount of energy is released. Then how this released energy will be utilized in this reaction. Now question arises, how this released energy, how this change in binding energy, which is responsible for the release of energy, will be utilized in this reaction. How this will be utilized, how this energy will be utilized, that can be observed from this equation. That can be observed from this equation. So consider this change. Proton is converting into neutron. Here this proton is converting into neutron. Whose mass is higher? Mass of neutron is higher or mass of proton is higher? Mass of neutron is higher. So we are aware that mass of neutron is higher as compared to mass of proton. So basically a mass is created here. When proton is converting into neutron, then some mass is created because mass of neutron is higher. So a part of this energy which is released, a part of this released energy will be utilized in creating a mass. How much mass is created? This will be equal to Mn minus Mp. Difference between the mass of neutron and mass of the proton. This much mass will be created. This created mass will be equivalent to some energy. How much energy? कितनी energy के equivalent होगा? This will be Mn minus Mp into C square. So a part of this released energy will be utilized to create mass, which is equal to the difference between the mass of neutron and mass of the proton, and we have converted this increased mass into energy. So a part of this released energy is utilized for this. Another thing is, this positron is created. Positron will have some mass. So basically, a part of this energy will be utilized for creating this positron. So this will be equal to MEC square. This will be MEC square plus mass of this neutrino. This neutrino is also created, so basically created mass will be m nu c square. So these three type of masses are created by this energy. So a part of this energy is utilized in creating three different type of masses. One, extra mass of neutron as compared to proton. Mass of the positron is created and mass of the neutrino is created. Here mass of neutrino is even less than mass of electron. Mass of neutrino is less than mass of electron. So basically we can neglect this. We are neglecting this. We have neglected this. So basically a part of this energy is utilized in creating these two masses, plus whatever energy is left, that will be in the form of kinetic energy of this positron plus kinetic energy of neutrino. So this energy is used for creating mass as well as providing kinetic energy to the positron and the neutrino. Now question arises, why this energy is not providing kinetic energy to this? Because the reason for this is, here this 7 and 13, this is not proton. Actually this is 7 and 13. This is at rest. This is considered at rest. And here on the right hand side, as compared to this positron and neutrino, this is a very heavy nuclei. Mass of C13 is very high as compared to mass of the positron and the mass of neutrino. So most of the energy will be carried, most of the kinetic energy will be carried by these lighter particles. You are aware from the classical mechanics that the kinetic energy carried by this lighter particle is always very high as compared to this heavy particle. But here the mass of this is very large as compared to the masses of these two particles. So most of the kinetic energy will be carried by this positron and this neutrino, and kinetic energy associated with C13 or this neutron here, this will be negligible. So this type of equation I will have. Now what is there? Here this is the total kinetic energy that is provided to positron and this neutrino. And this total kinetic energy is always fixed. So when this type of decay is taking place, then you will find out that beta particles of different kinetic energy are coming out. You will observe different positrons with different energies. And if we consider the positron with maximum kinetic energy, when will you get the positron of maximum kinetic energy? We will get the positron of maximum kinetic energy when the kinetic energy of this neutrino is 0. So out of the sample of positrons which are coming out, we will find out the maximum kinetic energy of the positron experimentally. And here if I substitute maximum, then this will become 0. So now my objective is experimentally, if I want to find out the radius of the nuclei with the help of this mirror nuclei method, then first we have to find out the maximum kinetic energy carried by this positron. In this positron emission process, different positrons carrying different amount of energy will be observed, and we have to find out the positron which is carrying maximum kinetic energy. We will measure that maximum kinetic energy and we will substitute here. This maximum kinetic energy carried by positron will be corresponding to the zero kinetic energy of the neutrino particle. So here, when I am substituting K maximum for positron, then second term will be 0. So this is my final equation. Now substitute this delta EC or replace the delta EC by this expression. Now I am substituting this expression here. So this will become E square upon 4 pi epsilon naught 3 times Z1 square minus Z2 square upon 4R equal to Mn minus Mp into C square plus MEC square plus maximum kinetic energy of the positron. So this is my final equation. Now by solving this equation, one can find out this radius of the mirror nuclei. This radius of the mirror nuclei. Here you can remember two things, that this term is equal to Mn minus Mp into C square. Its value is, you have to remember this is always 1.29 MeV. This is the value of this term Mn minus Mp into C square plus rest mass of positron is equal to 0.51 MeV. 0.51 MeV. In the question, he will provide you the maximum kinetic energy of positron. Substitute that value in MeV here and equate this term E square upon 4 pi epsilon naught. This will be 1.44 MeV Fermi into 3 times Z1 square minus Z2 square upon 4R. He will provide you a reaction, or he will provide you a set of mirror nuclei. So these Z numbers are correspondingly Z1 and Z2. So substitute here Z1 and Z2. Substitute here maximum kinetic energy of the positron or the electron which is emitted here in beta decay process, and you will find out the value of R, and that R value will directly be in terms of Fermi. So in this way you can solve this type of numerical. In this type of numerical, he will provide you maximum kinetic energy of this positron. Suppose this can have any value. Suppose this is 6 MeV. Suppose I am saying that this is 6 MeV. So I will substitute this 6 MeV here. And suppose they are providing me Z1 and Z2 like here. So this will be here 7 square minus 6 square. 7 square minus 6 square. And you can find out the value of R. And whatever R value will come, that will be in terms of Fermi. So in this way you can solve this type of numerical. So this is a very important method from exam point of view. Two type of questions can be there. In one type of question, he will provide you the change in Coulomb energy. He will give you a set of mirror nuclei and he will provide you the change in the Coulomb energy. So delta EC is provided. He will provide you the set of mirror nuclei. So Z1 and Z2 will be provided to you. E square upon 4 pi epsilon naught is 1.44 MeV Fermi. So by equating these two terms, we can find out the value of R. In second type of numerical, he will provide you the maximum value of kinetic energy of positron. Substitute that value here, substitute the value of Z1, Z2 here, and you will find out the value of R directly in Fermi.